Yeah, hi everyone. So now I am going to explain about energy methods, especially due to strain energy, as we discussed earlier. So first we will see the strain energy definition. What is the strain energy? So it is nothing but a stored energy at the time of application of a load on structural member. Okay, so now I am telling the definition strain energy. So what is the definition of strain energy? Means it is a stored energy in the body at the time of application of a load on a structural member. So whenever we will remove the load, that energy will be exerted. That means the energy will be shown by that structural element. That is nothing but strain energy. So this strain energy we are going to take in a 4 ways. Due to axial loading and due to bending loadings and due to shear loading and due to torsional loading or twisting or torque. Now see, there are a formulas for strain energy for each and every types of loading. So we are going to see the types of formulas due to different types of loading. So first case, strain energy due to axial loading. So here we are considering one element which is in vertical manner, where one end is rigidly fixed and another end is free end. There I am going to apply a load of P, and because of the application of this load P, it is going to deflected a little extent, which is nothing but dou L, and the overall length before deflection of that structural member is L. So this is the figure description. You have to write a theory in the exam about this figure description. Now see, here the basic formula to derive the strain energy due to any type of loading is nothing but strain energy is equals to work done. How that work done means, due to that load some deflection is happening, that is we are going to consider as a work done. That means work done by the system due to the load. So now we will go for a work done formula, which we are very familiar with this one. It is an average force into displacement due to load P. That means how much it is displaced due to the application of a load P. So average force is nothing but the load by 2, that is P by 2 into the displacement due to load is dou L. Okay, already we know that from basics, P by 2 into this dl is nothing but PL by AE, where I will write it this one as P square L by 2AE. Okay. See, I am not sure that this formula, this work done is complete structure. So I want to know for this complete structure. So I assumed this one as a elemental strain energy. That means du. If you want to know the complete strain energy, then you are going for a integration over the limits of 0 to L for P square into L by 2AE, where I will modify this formula as P square by A square into 1 by 2E into A into dl. Okay, see, we have to consider some differential form, so I will add that elemental to this length, so it will become a dl. Now we know that 0 to L, this P square by A square term will become sigma square by 2E into, see, this A into dl leads volume, which is nothing but dV. So finally a strain energy formula due to axial loading is equals to integration of 0 to L sigma square by 2E into dV. So this is the formula for a strain energy due to axial loading. Have a look at this complete derivation, then it will be clear for you. And here the two key points we have to remember is the basic formula where strain energy is equals to work done, and the second one is here average force you considered, where if it is a ductile material, it is having a ultimate stress, that's why you have to consider average force. If in case it is a brittle material, you have to consider direct force. Here I am writing for brittle, work done will be force. For ductile, work done will be average force. See, these are the points you have to remember. So we'll go for a second case, that is nothing but strain energy due to bending loads. Here some theory will be there. For every derivation you have to write some theory in the exam. That is nothing but where I am going to consider one beam. If it is going under the action of some bending moment loads, then some deflection will be happened, and here I am considering some elemental part of that beam. This is nothing but x length, and this is nothing but dx. So figure description, that means I am considering one beam, and in this one I am considering one elemental part which is having a length of x dx, and it is at a length of x from the one end point of the beam. Here this beam is going for a bending moments. Because of that bending moments, some strain energy is going to occur inside of that beam. So how you are going to calculate that strain energy due to bending load means, I have to consider the same statement where work done is equals to strain energy. I know the strain energy formula where U axial is equals to integral 0 to L sigma square by 2E into dV. So from this formula only I am going to explain about the strain energy due to bending loads. Here the reason why I considered this formula means, see, the bending moments are going to occur due to loads only. See, for example, if you consider any beam, if any loads are acting, then only it is going for a bending moment. So that means how the bending moment is occurring because of the loads only. So that's why indirectly I consider due to loads only that bending moments are occur, and due to that bending moments only strain energy is going to come. So that's why I took this formula. Now I want to write this formula in a triple integral manner. Why means I am going to move with volume, so that's why I took a volume integral. And from the basic bending moment equation, we know that where sigma by y is equals to m by I, that implies sigma is equals to m by I into y. So this value I am going to substitute in this equation. Then u is equals to triple integral of m by I whole square into y square by 2e into, here I am going to write dv as dA into dx. So finally I written formula like this from this one. Okay, now some more changes I am going to do, where a single integral I am applying for this term, that is m by I whole square into 1 by 2e into dx, and double integral of y square into dA. See, I changed formula like this from this step. Now it will be same, that is integration of m square by 2e into I square into dx. See, instead of this term I am going to write as Ixx, because we know that it is a second moment of inertia or area moment of inertia formula. Okay, so here they are not particularly saying it is about x axis or y axis, so you can avoid this I axis. Simply you can write m square by 2e into I square into I into dx. Okay, where I will get cancelled, then finally you will get u formula due to bending is integration of m square by 2ei into dx. So this is the formula for a strain energy due to bending loads acting. Next we will go for a third case, that is strain energy due to shear loading. Okay, so we'll go with the third case, that is strain energy due to shear loading. See, here I am considering one member which is in a rectangular shape, whatever may be, you just take one shape. So due to the action of the loads, what type of loads means shear loads, so definitely it is going in this direction. At the bottom surface it is going in a opposite direction. So due to these forces, what will happen means definitely some angular deformation will occur in the structure, that is going to shown by with these dotted lines. And here this angular displacement, that means the deformation, I am going to shown with phi. This is the figure description for a strain energy due to shear loading. So the same formula again, work done is equals to strain energy, where directly we will take strain energy is equals to half into the load acting is Q, and here the displacement due to that load we have to consider as a d phi, or else for simple case you can consider dx for no confusion. So I will write, for convent purpose I will consider it is as a dx. If you are not going to confuse, you can take d phi also, no problem. Then you just take the length is x, this length is x. Now already we know that this term generally delta L, that is elongation is equals to PL by AE. It is for a direct loads. Here we are dealing with the shear loads, then it will change that dx instead of P. What is the load acting? That is nothing but Q. And what is the L? L is nothing but x, you have to consider overall length, and A is AR, that is reduced area, and the E instead of E, Young's modulus, we are going to take shear modulus G. So now I am going to substitute this value here. So then U is equals to half into Q into Qx by AR into G. So where Q is load, X is the overall length, AR is reduced area, shear is G is nothing but shear modulus. Then you just consider this is for a elemental part. Then du is equals to Q square dx by 2 into AR into G. If you want to know for complete structure, then you have to go for a integration of Q square into dx by 2 into AR into G. Here the same thing we have to use the concept where we used in this form. So here P square by A square, like that we done, right? The same thing here also we are going to do. That means integration of 1 by 2g as it is, and Q square by AR square into AR into dx. Then U is equals to integration of shear load by area, which is nothing but shear stress tau square by 2g, that is 2 into shear modulus, where area into length leads volume, which is nothing but dV. So finally the formula for strain energy due to shear equals to integration of tau square by 2g into dV. So this is the formula for a strain energy due to shear loading. Next we will move to the concept of strain energy due to torsional loading. So coming to strain energy due to torsional loading, so go with some theory where I am going to consider one cylindrical part or one circular bar. It is undergoing for a torsional moments, or else twisting, or else it is undergoing for a torque. See, I am taking here in the same direction, or else you want to consider like this also. You have two cases, there is no issue, but the same derivation for both. So, and here also I am considering some elemental strip which is having a length of delta dx. Sorry, not delta x, it is a dx, and it is at a distance of x. Why here we are considering means, see, this leads to moments, so that's why this length is helpful while you are doing the derivation. So that's why we are taking this length x. Okay, so as usual I don't want to tell, the same formula, work done is equals to strain energy where u is equals to half into load into displacement, that is equals to, here load is torque load, that is T by 2 into displacement is nothing but dx. So as we discussed in the last section, how you are going to write this one, okay, with the help of dl is equals to pl by ae. So then coming to torsion moments, that means I'm coming to torque loading or torsional loading, then dx you just write it as a t into x by, t is nothing but torque load, that is nothing but p, so length is x you are considering because due to the moment, and a, instead of a you are going to consider some torsional constant k, and instead of Young's modulus you are going to consider shear modulus g, because some shear deformation is also going to happen because the torque is or torsion is going to acting along the skin of any element or any structure. So that's why you have to consider a shear modulus g only. Here the only change is, instead of area you are taking one constant term which will give effect at the time of torsion, that is nothing but k, which is nothing but torsional constant. So I am going to substitute this dx value here, that is nothing but t by 2 into tx by kg. Okay, so again the same concept, if you are going with some elemental part, then it will be integration of t square by 2 kg into this x will become elemental length, that is dx. Okay, now the total strain energy due to torsion is that u torsion is equals to integration of t square by 2 kg into dx, a simple formula, no need to struggle for this one. So this is the final formula for a strain energy due to torsional loading. So these are the 4 cases we have in a strain energy method, which are nothing but, this is the first one, and this is the second one, and this is the third one, and this is the fourth one, where axial load, bending moment, shear and torsion, depending upon the cases given in the problem, you have to use that respected formulas. So coming to practical point of view, generally we have a types of frames. You know what is a frame? Frame is nothing but, simply I will tell that it is like a skeleton. See, without skeleton we can't stand, our body can't stand. Like that, for any structure one skeleton is required. That skeleton we technically call it as a frame. That means a supporting structural member, a huge supporting structural member which will give supports to the complete body, which is going to form one shape, and it is helping to stand. So that is nothing but a frame. Here no need to go that much thorough with frame, but here why I am taking means, here we have to consider 2 types of frames, which are nothing but plane frame and second one space frame. Both are rigidly supported. So coming to plane frame, coming to space frame means, first if you are taking plane frame, see the concept of this plane frame and space frame, what they are telling is both are the same frames where the joining of n number of elements or members, but how in which manner they are joining together, that concepts will reveal the plane frame and space frame. For example, you take a one member like this. So here these two parts I am going to give a proper structure by joining with some elements. What are that elements means? This type of vertical. So with the help of these elements, this one we will call it as a elements or members. With the help of these members, this structure will become a frame. Okay, so how these members are joined at these points, this one we will call it as a nodal points. So this will plays a major role because here joining is going to happen, so that's why these nodal points are very important. So how these things are going to attach at the sections, that is very important. Okay. So these are like a separate joint, it's like a point to point joint. Point to point joint phenomena is happened. So this type of frames we can consider it as a plane frame. Then coming to the space frames, you just take the same figure and the same elements you just go take. Here the members you are taking, a simple space frame I am showing. Actually this much of simple space frame won't be available, but for our understanding purpose I am showing a very simple frame. See here the nodal points. How the nodal points? See, coming to plane frame, the nodal points, that means the joining part of this horizontal member and vertical member are point to point, separate. But see here, one more some helping component will be there, which I shown in that figure in our class, that zoom app class. So that type of structure will be there. In that one we will insert these two elements. The same manner here. So what is the advantage of that space frame means, see, the joints will reduce. The joints will reduce in a space frame compared with a plane frame. Okay, so if the joints is going to reduce, then it is getting some more strength. So that's why space frame is sometimes more useful. And here the load is pointed at certain point, and here load is distributing equally. So the complete load, for example, the P load is acting on this complete frame, that will be as P for first one and the P for second one, like that it will come. But coming to space frame, the same P load is acting. How that P will be means, it will be like P1 plus P2 plus P3, and P1, P2, P3, that all are equal, where that P load is equally distributed among the each and every member. Okay, so those are the advantages of space frame. Depending upon the given type of frame in the problem, you have to go with the formulas. So how the formulas is going to change means, see here only direct loads will act, because there is no chance to get a torque here. But because of the combination of these points, here we will get a chance of torque.